Welcome back everybody. What I want to talk about today is weather and how weather actually has an effect on coral. And not only do I want to talk about weather, but I also want to talk about climate. You recall that weather is local, climate is more global or regional, but it's also long-term. Weather tends to be short-term disturbances in the local atmosphere. Climate can be a little bit longer term and usually over a little bit larger scale. Both these affect corals, and we're going to talk about how those systems work in the context of oceanography. You'll recall last time we talked about some of the magical properties of water. Water is one of those materials I think about, substances I think about that I just can't help but smile when I think about it. I mean, it's not only is it a universal solvent, so it's got amazing chemical properties where the physical polarity of that molecule allows it to break off ions from different substances and deliver them not only throughout individual organisms so they can get nutrients and keep their cells functioning, but also around the whole planet. So, it's responsible for dissolving mountains and bringing minerals from the mountains back into the ocean so that life can thrive down there. We talked about how without plate tectonics, without those mountains being pushed back up, we'd end up with a big sink of nutrients that would not be mobile, wouldn't be able to get to life. So all these things come together in kind of a magical way. But what I'm going to focus on today is more the physical properties of water and how those latent heats are very good at moving heat around the planet. It actually has a long-term effect on affecting the global thermal regulation. One of the important physical properties of the planet that is important to consider both in how and where coral reefs live and how global weather systems and climate works is the fact that, strangely, our planet is tilted on an axis. Our axis is not straight up and down. It's actually tilted at 23.5 degrees. And curiously, the tropics, what defines the tropics is that dip of the planet. So the tropics occur where at the solstices the sun is directly overhead. So first we have the Tropic of Cancer in the northern hemisphere, and on June 21st the sun will be directly overhead there. And the southern hemisphere, we have the Tropic of Capricorn, and on December 21st, the sun is directly overhead there. During the northern hemisphere summer, of course, we're going to have full daylight, 24 hours of daylight at the North Pole and in the polar regions. And in the southern hemisphere, we're going to have all night during the northern hemisphere summer, and vice versa when 6 months later. Interesting things also about how climate is affected. In the northern hemisphere, there's more land mass. Land mass heats up faster because it's not water, doesn't have the same latent heat, it doesn't have the same heat capacity. So weather and climate's just different in the northern hemisphere than it is in the southern hemisphere, and that's something that we'll talk a little bit more about later, or something to consider as you go forward in your projects. At higher latitudes, the sun, these are all the same amount of sunlight coming into the planet, but you can see how that heat is actually distributed over a much broader area as it comes in over the northern latitudes. So it's not as effective as heating up 1 square meter or whatever area of temperature, but at the pole, at the equator rather, it has a direct hit. So all the heat that's coming in there goes to heating up a much smaller surface area. So keep that in mind. But let's go back and consider the heat that's coming into the planet. Look at the heat coming into the planet. We're going to talk on this briefly. We'll come back to when we talk a bit more about climate change. But if you consider all the solar radiation that's coming into the atmosphere, it's quite a bit. It's enough to power the planet if we need to forever. It's perfectly sustainable. However, how we actually manage that heat coming in is a different story. A lot of the heat gets reflected back out as short wavelength radiation by things like clouds and land surface and glaciers and even water for a certain extent. Not so much water because it almost is black, but that's another story. But once the heat gets absorbed into the planet, it gets radiated back out as long wavelength radiation. Now that can usually blast through clouds pretty easily. It doesn't get scattered by clouds and reflected back in. What's responsible for most of the global warming is that absorption by carbon dioxide in the atmosphere. We'll come back to that. Okay, this somewhat complicated diagram is actually pretty important and pretty fascinating. Now, if you think about how the planet should work, if you have it heating up in the tropical areas between 23.5 degrees north and 23.5 degrees south, that's where the hottest temperature should be, and where it's going to be colder during part of the year and these higher latitudes, that's where the coldest air should be. So we should end up with one big circulation cell that starts at the equator-ish, goes all the way to the poles, drops back down, and then the wind should sneak itself, or the air should sneak itself back down to the equator, heat up again, etc. Why doesn't it do that? You can tell in this diagram here, we have these westerlies, which everybody knows the trade winds that go from the east to the west. That's what Columbus took from Spain and why he ended up being in the Caribbean rather than landing in Plymouth Rock in the United States, or why a lot of the trade routes went from Mexico towards the Pacific, and actually more like whaling routes and that sort of thing. However, what happens is you end up with these different cells. At the region between the equator and about 30 degrees north, you have what's called the Hadley cell, and that means we have a low pressure zone at 0 degrees. As that air descends back down, as it cools off and descends back down, we tend to have high pressure at 30 degrees north. And then we have above that a Ferrel cell that starts at the high pressure zone at 30 degrees north and goes up to a lower pressure zone at 60 degrees north. These low pressure zones tend to have clouds. We're evaporating water off the ocean, and it comes up into the atmosphere because it's going from higher pressure to lower pressure as it gets evaporated up, and it condenses in the atmosphere and forms clouds. So the weather tends to be kind of crappy at 60 degrees north as a rule, and at about 30 degrees north, or 30 degrees south for that matter, it tends to be a little bit cooler and drier and sunnier weather. So the question is, why does it form these three cells? Well, it's got to do with the Coriolis effect. I'm sure you guys at least heard about this in high school, perhaps not. But because the Earth is actually spinning, things get deflected. I can think of a couple of examples, and I'd like to challenge you guys to think of some examples too to demonstrate this. But if anything that's moving in a straight line in the northern hemisphere will get deflected to the right. If it's moving in a straight line in the southern hemisphere, it will get deflected to the left. So these hypothetical winds, these cold winds that should be descending from the poles to the equator, get deflected the whole way. And they never make it down there. They just end up going always deflected to the right, so they end up forming these circles. They end up forming these gyres or cells. And they can't make it all the way down because they're constantly being deflected. It's a good thing too, because what it does is it actually sets up these currents in the world's ocean. These currents are important for so many different things. If you look at the middle of the Pacific Ocean there, you can see what they call the North Equatorial Current and the South Equatorial Current. And between that, right under the North Equatorial, you can see the North Equatorial CC, and CC stands for countercurrent. What happens is you end up with these winds, these westerlies or the trade winds that are constantly pushing water from the east to the west. As that water gets pushed, literally pushed across the ocean, it piles up water on the western side of the basin. But then that water's got to go somewhere. Some of it goes to the north, some of it goes to the south, but there's actually a zone of divergence right at the equator where you end up with them going in opposite directions, and there's a gap in between. So some of that water actually flows back along that gap to the east, and that's what the countercurrents are. And these are very important when considering the weather phenomenon known as El Nino, which we'll talk about in a minute. But you can also see these large gyres. You can imagine warm water going up through the northern Pacific Basin along the Kurashiro Current to bring warm water to Japan, keeping it rather comfortable temperatures, and then finding its way back around through the North Pacific, and then cold water comes back down along the California coast. California is one of those ironic places because it's always so beautiful, sand beaches, and you see people frolicking in bikinis and shorts, but the water's always really cold. Most places you want a wetsuit to go in the water, even in Los Angeles and especially in San Francisco. Ooh. But there's another reason why the water's so cold there, and that has to do with the fact that the California current is going south. It's always getting deflected again to the right, or in this case to the west, and again you end up with a gap. It's pushing water, in that case offshore. You've got to fill that gap with something, and that gets filled with colder water. Similarly with these equatorial currents, you end up with water always being deflected to the north and to the south, and that something's got to fill that gap, so you end up with colder water, nutrient-rich colder water, which is actually important, being drawn up at the equatorial regions. Another example of how water is moved around at kind of a different pace has to do with this thermohaline circulation we started talking about before. You end up with this sea ice that's being formed at the higher latitudes, creating this cold, dense water that then snakes its way along the bottom of the oceans. Eventually, it's got to be replaced. You can't just make cold water. Nature abhors a vacuum, so you end up with warm water that gets drawn into filling that gap. But this global conveyor belt, global heat conveyor belt, is responsible for regulating a lot of the global climate. And one of the big concerns with climate change is that this bad boy could actually shut down. And they believe that happened at one point during the Little Ice Age. I believe it was like the 15th or 16th century. where Europe pretty much froze, and London was really cold, cold enough that you could skate on the Thames. And I don't know when last time the Thames was frozen. It might have been about 500 or 600 years ago. So this is a big deal. If this guy shuts down, we're going to have some interesting changes that happen in the planet. Another phenomenon that has to do with these currents is the El Nino and La Nina cycle. During El Nino, what happens is, you can see this is a graph of sea surface temperature, or anomalies in sea surface temperature. During El Nino years, that equatorial countercurrent area is not so much cold, but it actually gets warm. During La Nina, which is like an exaggeration of regular times, it gets quite cold, as you can see from the blue area in this diagram. This is a diagram that shows what's going on in these situations. In the normal times, you have trade winds which are driving water from the east to the west. Warm water piles up in Indonesia and causes a lot of rain, so it's always very tropical, steamy, hot, jungly, and that sort of thing. The same case on the other side of the basin in South America. We have water that's coming out off of the South Atlantic Ocean. That hits the mountains in South America and then falls as rainfall in the Amazon basin. But on the other side of those mountains, it's a desert. There's not enough moisture left because it's all been dropped in the Amazon basin. So you end up with a very dry area over there, and the cold water gets upwelling because you have the cold currents are being pushed off there. Water gets replaced there with cold, nutrient-rich water from that side. Fantastic fisheries and nice, cold, dry temperatures on the west coast of South America. What happens during El Nino years, though, those, for some reason, we don't really know why, but those trade winds kind of die off a little bit. They're not strong enough. So all that warm water rushes back across the Pacific Ocean basin and causes that warm, moist water to be on the eastern side of the basin, which means you have rainfall in places where you usually don't have rainfall. And that can be a problem where you have lots of flooding, landslides, and the like, and fisheries get threatened because you don't have these nutrients that are upwelling in these areas, so there's not enough stuff for fish to eat. So it's a big deal and can cause some big problems in these areas. Doesn't so much affect the tropics because the tropics are safe. Let me think about that. I'll come back to that. Okay, another important feature that we have to talk about in areas of the tropics where we do have coral reefs, and one of the big stressors on coral reefs are tropical cyclones and storms. And put this graph up here because, as the story goes, what you need to form a tropical cyclone is just a very small low-pressure zone. It could be caused by a butterfly flapping its wings. But this low-pressure zone starts in these areas like the deserts of South America. As these trade winds push the these low-pressure zones over water, the low-pressure zones start picking up moisture. And remember, going back to the physics of how water works, as it evaporates water, it's pulling up the latent heats in those waters too. And as it cools up, as it gets into the upper atmosphere, it starts to condense. And what happens with condensation? Reduces latent heat, produces latent heat, releases that latent heat in the form of wind. Wind starts blowing in one direction, gets deflected by the Coriolis effect, eventually it starts spinning. And it's always getting thrown out in different directions because it's always being deflected to the right. Creates a bit of a vacuum, which then sucks more warm, moist water up into the upper atmosphere, which brings more latent heat into the atmosphere, which generates more winds, which drives the wind stronger, which pulls more water up into the upper atmosphere, which then causes more latent heat producing release and drives more winds. This will continue as long as there's a source of warm water. The only way you can kill a storm like this is to bring it over land, to remove its fuel source, or to bring it into cooler water. And that's how a tropical cyclone is formed. Next time, we'll start talking about how the physiology of coral reefs work. I'm going to put in one more slide. Pause for a second. Next week, we'll start talking about how the actual animals of coral reefs have evolved to respond to these stresses in the environment. These stresses can be anything from freshwater stresses that go with rainy seasons and the like, to other stresses like temperature stresses when you have increased or decreased water temperatures. But also, what I really want to focus on is energy and how energy, wave energy and the like, affects how these reefs are structured and the different structures these reefs have evolved to function in these different energy environments. Thanks, and we'll see you next time.